Okay, so we're talking about static equilibrium, something I think we're pretty familiar with, but we need to include some stuff that we just learned from chapter 8 into the idea of equilibrium. Basically, what static equilibrium means is that there's no motion. So we studied translational motion all the way back in the first couple of chapters, right? And then just recently we studied rotational motion. So now we can combine those two ideas, translational and rotational motion, and we can write down conditions for static equilibrium. Right? So can anybody tell me what are the conditions or condition for static equilibrium in the translational sense? So no translational motion. So you can write your answer in the chat or you can speak up. Translational motion. So what are, probably should put is/are. Okay, and I just got a message, so maybe that's the important message. Okay, yeah, it was. Okay, so do you guys have an idea? So what are we thinking? What is what is the condition? What is or are the conditions for translational motion? I should have probably put equilibrium.
No net force.
No net force. Okay, so the question did make sense then. So what is or are the conditions for equilibrium? Let's add that in there. For translational motion. Okay, so maybe let's switch the color here. So no net force. Net force equals 0, right? And how do we calculate the net force on an object? How do we calculate the net force on an object? Maybe somebody else can answer. Summation of all the forces, exactly. So good, so we can translate this over here and we can say the sum of all of the forces, however many we have. And we do remember to put our vector signs here. And then all the sum of all the forces should be equal to 0. That's net force equals 0. But suppose we have, a problem that we're trying to solve for something, right? This object is in static equilibrium. Maybe there's an unknown force or something like that. Probably this vector equation is not going to be the best bet in solving for, the unknown force, right? So what would we want to do? How would we change this equation from vectors to not vectors? What would we do?
Absolute value?
No, so absolute value, that would mean like the magnitude of the vectors. No, almost though. So it is something, we got to do something with the vectors to maybe break them down into smaller pieces. Let's see, we have a chat here. Use the magnitude of the x and y. So let's not say magnitude of the x and y components, but just the x and y components themselves, right? Because if we take the magnitude, then we would lose a minus sign where we might need that minus sign to be. So we want to just use the components of the vectors. So we can break this down into maybe two equations. We can sum up all of the x components equals 0, and we can sum up all of the y components equals 0. And now, if we were working in 3 dimensions, we could also have z components, but we always avoid, 3 components. It's just extra algebra is really all it is. Okay, so those are the conditions for static equilibrium for translational motion. Now, if you guys remember, and this is just a subtle detail here, this isn't very important for problem solving, but just a subtle kind of physicsy detail here, is that the force is proportional to acceleration, right? And we're saying that static equilibrium is no motion, but you can have constant velocity and all of the forces acting on you are 0, so you're not accelerating, right? It's actually pretty important that that's the case, because it's impossible to distinguish between somebody else's motion and the motion that you have, right? This whole idea of relative velocity, right? And inertial reference frames. But oftentimes we'll do problems in which nothing is actually moving. So the velocity of those objects is 0, just so that way things a little bit more familiar, right? Because we're used to thinking of maybe something is at rest on top of a table, right? It's not moving, right? But really it's moving as the earth spins around. It's actually moving really fast, right? So yeah, just a little subtle detail there. Okay, so there's another condition or conditions now for rotational motion. So who wants to take a stab at that? So what are or is the condition or conditions for equilibrium for rotational motion? So who wants to take a stab at that one? What is or are the conditions for rotational motion, or for equilibrium for rotational motion? Okay, we have a chat. Net torque equals 0. Christiana has already given us an answer. Maybe somebody wants to say if they agree or disagree with that answer. And let me try and follow up while you guys are thinking about that. Um, did I um, Okay, so hopefully we all, I don't see any chats, but hopefully we all agree. Okay, a couple of us agree there. So we might end up rescheduling the observation. I'm not exactly sure, so I'm just asking right now. So it is the net torque equals 0. And now we do know from chapter 8 that torque is indeed a vector, and in reality we would have to include a vector sign here for the net torque equals 0. But we only ever do problems in which the torque is going to be plus or minus, right? So it's only going to be positive or negative. We're not going to deal with like three or two or three components of a torque vector. But remember, you use, and I don't know if you guys can see this for me, but you use this right hand rule, right? You have to make sure you use your right hand. So if you guys, let me stop sharing for a second. Stop sharing for a second so I'm a little bit bigger. Just to remind you, so this is my right hand. I don't know if you guys see this as my right hand, but this is my right hand, I promise you. If you want to know the direction of a torque vector, you use the right hand rule. So you can wrap your fingers in the direction of motion for a rotational motion. So for example, like if you're riding your bike, there was a question on the test, right? If you're riding your bike and you're moving forward, your wheels are rolling this way. So my fingers wrap in that direction. It means that the direction of the vector is to the left. So that was the answer on the test. So the angular momentum vector is to the left. If there was a torque, which of course there are two torques actually on your bicycle wheel, one due to the friction force that is actually moving you forward, right? And then one due to you pedaling. It's due to the chain that's attached to the wheel, right? So there are two torques there, and those torques have opposite directions, right? In order for you to travel forward with constant velocity. So you use your right hand, and you always take your fingers and put them in the direction of the rotation, and your thumb points in the direction of the vector for that. So if something's like rotating like this, then the torque vector, or excuse me, the like the angular velocity vector would be this way. If it's accelerating in this way, then that means the torque vector would be in that direction, right? If something's rotating like this, but it's slowing down, then the torque vector would be in the opposite direction. That wasn't such an important topic in the last chapter, but it's definitely something to keep in the back of your mind. That torque is definitely a vector, but we always do problems where it's treated as just a number because everything is in two dimensions for us. Okay, so let me go ahead and share the screen again. And we'll go ahead and finish this off then. So if the net torque equals 0, of course that means, maybe I should have switched to blue a little bit earlier there, that we can sum up all of the torques in our problem and set it equal to 0, right? So net means sum. And so there are our conditions for equilibrium. Maybe let's highlight them here in red. These are like the three important equations that you want to like always, just this is the first thing that you do, is maybe you write these on the side for a problem, right? So just to remind yourself, like, okay, this is what I'm going to do for this problem. I know this is a static equilibrium problem, right? And so I'm going to sum up all the forces and set them equal to 0. I'm going to sum up, x and y components, and then I'm going to sum up all the torques and set that equal to 0. And you always put equal 0 when you're doing static equilibrium. This is like kind of a common mistake I see with students. This even happens in, this happens with my other students that I have like this semester for electricity and magnetism. We do Kirchhoff's laws, which you guys will learn next semester. And Kirchhoff's laws always have an equal 0 at the end of you like write some stuff down, and then you're supposed to always put equals 0. And there's always students who forget to put equals 0, and then they're kind of confused. They're like, oh, what do I do with this? I don't even have an equation, right? You got to make sure you always put your equals zeros whenever you write this stuff down. Okay, so always equals 0. And that's for static equilibrium. So if it's not static equilibrium, some of the forces should be mass times acceleration, right? Some of the torque should be moment of inertia times angular acceleration. But since we're doing static equilibrium, always equals 0. And I'll try to keep reminding you guys to do that. Okay, so do we have any questions about that, or that's pretty clear? Can you give me a thumbs up if we're ready to move forward? Okay. All right, looks good. So we're just going to jump into some examples. We're going to take things, kind of slow since we just came off the test and we have an extra lecture here. So we'll just jump right into some examples here. So here's a nice example. This is like a nice warm up here because in this particular example, we don't have any torques. So we're only dealing with forces in this example. So I'll go ahead and just get you started here. You're only summing the forces and setting them equal to 0. Okay. So what are we doing though? What we have here is a figure which is showing a chandelier hanging from the ceiling. And we have 2 cords that are supporting that chandelier, right? So those cords have to support the weight of the chandelier. Of course, if you're an engineer, then you're going to probably have a better design than what's shown here in the figure, but this is what we have here. And so what you're going to do is you're just going to sum up the forces, sum up by components, right? So X and Y components separately. And you're going to solve for the 2 tensions there in the cords, okay? There's 2 tensions. We have the tension, which is FB, and we have the tension FA. And it looks like you don't have enough information at first glance, right? You're looking at this, we have 1 known force and we have 2 unknown forces. But actually, it turns out there is enough information here because it's in static equilibrium. So because those summations of forces equal 0, we actually have enough information here to solve this problem. Okay, so go ahead and start now if you know what to do. Start summing up those forces for the X component and then sum up the forces for the Y component. And take note of the coordinate system that we're using here. So take to the right to be positive X and take up to be positive Y. Okay, so I'll give you guys some time to work on that. Let me try and follow up with the evaluation business here. Okay, so it looks like we're going to reschedule that evaluation. So maybe next week sometime, probably there'll be an extra person in here, like evaluating my teaching. So let me know if there are any questions. I'll keep an eye on the chat here. Remember, when you sum forces, I think a lot of students like to do something like this. They indicate the direction that they're going to take to be the positive direction. And then say something like, okay, I'm summing the X forces to the right as positive, I got to remember to set this thing equal to 0. Right? I only have 2 components in the x direction. I've got FB, which is all in the x direction, right? And I've got the x component of FA. Maybe you guys can help each other out. You can say, how am I going to calculate, and we can just put this in the chat, how am I going to calculate FAX component? What is that going to be equal to? We have to kind of remember our trig here. What is FAX going to be? Help our fellow students out here. Let me actually clean this up a little bit. Let's bring this down here. If you get an answer for one of the components, go ahead and you can put that in the chat, and that helps other people check their answers, right? And then if you made a mistake and people get different answers, then you can kind of go back and double check your work, right? Okay, what's our progress on this one here? Give me a thumbs up if you're working, you know what you're doing, just so I know. If I need to help, just let me know. You go ahead and write a little bit more for those of you who maybe are looking for a little bit of help here. So if I sum the forces in the x direction, that's going to be FB is going to be positive because it's pointing to the right. And I'm going to subtract FAX because the x component of FA is pointing to the left. So we have to have that minus sign in there. And then don't forget equals 0. So just put equals 0 there. Okay. Now, the next thing to do, right, would be to sum forces in the y direction. So the up is positive. So sum the y components, set it equal to 0. Is that good? Does that help you guys? Those of you who didn't give a thumbs up before, can you give me a thumbs up if now you're a little bit better on that? Okay. I'll go ahead and do the y components now too. Let's use the black here again. So in the y, we have FAY is up, is up. So that's going to be positive. But we're going to subtract from that the 1,960 newtons. That's the one thing that's given to us, right? That's basically the weight of the chandelier, right? Measured in newtons. If you're wondering how much that is in pounds, it's about 4.4 newtons per pound, something like that. So this thing is pretty heavy, like 200 kilograms, right? So it's like 2.2 pounds per kilogram, roughly. So this tells us right away what the AY component is. It has to be 1,960 newtons. You guys with me? Should I keep working on it more? You guys have a sense of what to do now? Give me a thumbs up if you want me to just keep going through it kind of slowly on the board. Those of you who kind of you've got a sense of what to do, just feel free to just work ahead. That's fine. And then if you get an answer or something, put it in the chat. Okay, so some of you want me to just kind of keep working on it. Just work ahead if you know what you're doing, and that's fine. But if you want to follow along, that works too. There's a little bit of a trick here because this equation FB minus FAX, this tells us that FAX is equal to FB. Right? So if we want to know what FAX or FB is, we have to know something. We have to know some additional information about the components of FA, right? And we do know something. We know that there's a 60-degree angle here, right? So since there's a 60-degree angle there, let me just quickly draw like a little picture here. Since this is 60 degrees, this one is also 60 degrees, right? That's the, what's it called? Alternating interior angles, something like that, from your geometry class that nobody remembers. So that angle is 60 degrees. So that means that FAX is equal to FA cosine theta. And then of course we also have FAY is FA sine theta, right? So we can use trig to figure out those components. Now really what we have to actually do is we have to figure out the magnitude of FA, right? Because we know what FAY is, but we don't know what FA is. So that's where the trig comes in. So we know FAY right here, I'll highlight in red. So we should probably use this formula here to figure out what FA is, the magnitude of FA. So maybe somebody can help me out with their calculator. So FA will be equal to FAY divided by sine of 60 degrees. Well, let's just put sine theta here. And that's going to be equal to 1,960 newtons divided by the sine of 60 degrees. Maybe somebody who got a little bit ahead can give me that numerical value. Okay, cool. So 2,263. Let's go ahead and maybe round it to 3 sig figs. So 2,260. Give me a thumbs up if you're with me on that. Did that trig make sense right there? So we're going after the magnitude there of the vector. Okay. Once we have FA magnitude, then we can get FAX, right? So it's the same angle. We just need to take this 2,260 and multiply by cosine of 60 degrees. And maybe let's change the colors again so we don't get, it doesn't look too cluttered here. So FAX is now going to be equal to FA cosine theta. So just rewriting what we had over here in blue. So this is from the red equation over here, right? So this one. This is from the blue equation. Okay. So we take that 2,260 newtons and we multiply by cosine of 60. Cosine of 60 is just 1/2, so I don't need help on that one. So we get 1,130 newtons. Go ahead and let's go ahead and maybe like box all our answers here. Maybe purple. Okay, so we now have FAX, we have FAY, and we have FA's magnitude, right? And we know the angle for FA, so we pretty much know everything about FA. And then we just have to revisit this equation right here. FAX equals FB, right? So we've just got FAX, that's the one down here at the bottom, the 1,130 newtons. So FB has to be equal to that 1,130 newtons. So maybe we can put it right here. So this one is 1,130 newtons. Okay. All right, let's go ahead and gather up all our stuff here, right? So we can write it down nice and neat here in the notes. So we have that FAX. That one is 1,130 newtons. FAY. That one is 1,960 newtons. FA, the magnitude of that force, is 2,260 newtons. And finally, FB, that's the tension in that horizontal cord. That's going to be the same as FAX, so 1,130 newtons. There we go. Those are all of the tensions there in the string. So hopefully you see, maybe it was a little challenging to get started on the example just because it's like first time you see it, but hopefully you see that these problems are fairly straightforward in how you go about solving them. And we'll talk a little bit about a problem solving strategy here that we can kind of go through in a minute. But for now, we're kind of being given everything in terms of a figure here. So you probably can already guess maybe one of the first things you'll want to do is draw yourself a picture and kind of label everything like a free body diagram, right? So we'll talk about that in a minute here. But for now, we have another example. This example here was all forces, right? There's no torques here. It's just tension in chords. Let's do an example now with no forces and just torques, right? So no forces in the next example, just torques. Is everybody, give me a thumbs up if we're all done copying this stuff down that I wrote here. I can just go on to the next screen here. Leanne, Jew, Matthew, Sammy, we good? Leanne, you there? And maybe she's not here right now. Okay, second example. This one we're gonna go, don't be alarmed here. It's an analytical solution here, but it's very straightforward, okay? Solve for the ratio big R divided by little r, which is sometimes called the mechanical advantage for the lever in the figure, okay? The lever in the figure over here on the right here, right? You're trying to use this metal bar and a small rock as like a pivot point to lift up this much larger boulder. So this is like standard practice. This is what people thousands of years ago knew, that you could use like little lever systems like this to multiply your ability to lift other objects, right? And so this is like actually really ancient physics that people kind of understood long before they even knew anything about like force or, like weight, mass, or anything like that, right? So this is kind of like ancient physics here. So we have a lever arm, which is essentially a long stick. You can really just think of it as a long stick or rigid rod if you want to put it in physics language. It's a rigid rod, and you stick it under a large object, and then you put maybe like a smaller object underneath that rod close to the big object. Notice right here, this little rock beneath that rigid rod is closer to the big rock than it is to the person. And then the person is going to push down with a force to lift that big rock up. And that force, what we're going to see is basically, instead of being a force that's lifting the rock, is actually a torque on this lever about this pivot point. And ultimately, if we have static equilibrium, we can solve for how much of a force we would need to push down so that that torque would balance the torque given by the force, which is the weight of the boulder, okay? So it's kind of like getting a connection here between torques and forces, right? We have two torques working against each other. And if we use the conditions for static equilibrium, well, we know that if we push just a little bit harder, then we'll be able to lift the rock. So we can solve for static equilibrium, but really the static equilibrium is helping us get something that's not static, right? Which is to like lift the heavy boulder up. So that's the idea here, right? So we use the conditions for static equilibrium to figure out how to move this thing. All right. So if you know what to do, go ahead and work on it, okay? I'll go ahead and kind of inch along here. So those of you who are kind of a little bit confused, like what to do, I'll do the same thing as last time. I'll kind of inch my way through it nice and slow. So if you want to follow along and try and just kind of copy what I'm doing to get kind of warmed up, that's fine. But let me give you guys some time to kind of get started on it. Again, just reiterate what I said in words earlier. This is a problem with only torques. So we're summing the torques and we're always setting them equal to 0. Okay, we're always setting them equal to 0. Static equilibrium equals 0. So that's the starting point there. And just to remind you, torque is force times lever arm. So force times lever arm. In this case, the lever arm is going to be big R for the person and little r for the rock. Just want to give you guys a little bit of a hint here. Best to calculate the torque about the pivot point, right? About the small rock there. So calculate the torque about that small rock. Give me a thumbs up if you're working ahead. I would really expect more than one thumbs up. Okay, give me a thumbs up if you want me to like kind of start. You've thought about it enough and you don't know what to do. You want me to start working now? Give me a thumbs up if you want me to start. Okay. So several of you want me to kind of go through it. I hope even though you want me to go through it, you're trying something, because you really need to to get in that habit of try something. But here we go. So I'll kind of inch my way through it now. So I want to calculate torques here. So it's force times lever arm. But I know that if I sum the torques and it equals 0, I have to be careful about my signs. I have to have a positive and a negative torque, right? So if I look at this, I see that the boulder kind of wants to rotate. From my perspective, looking on my screen, the boulder wants to rotate this way, the system this way, and my lifting force, my lifting force wants to rotate it the opposite way, right? So definitely there's a minus sign between these two torques. Doesn't matter which one I make minus, there's only 2 of them. So as long as one of them is minus, then I'm good. A nice way of thinking about it is maybe counterclockwise is positive and clockwise is negative. So that's one way you could do it. So let me go ahead and write that. So I'm going to take counterclockwise counterclockwise to be positive when I sum my torques. Let's go ahead and change colors here. Okay, so if that's the case, the boulder is the one that wants to rotate the system counterclockwise. Obviously it can't because the earth is in the way, right? But that's the idea. That's going to be the weight of the boulder. This is a force, that's the weight of the boulder. Times the lever arm, which in this case is lowercase r, because this system is going to rotate about that small rock. That's the pivot point for this system. So that boulder's force wants to rotate things counterclockwise, that's positive. The force of the man there is going to be wanting to rotate the system clockwise, so that's going to be negative. So minus the force of this person here, and times the lever arm again, and the lever arm for this force is big R. Big R. And again, that's the distance from the pivot point to where the force acts. Now, one thing that you might be wondering here, and I'm kind of wondering it myself too, why they haven't given us any angles here in this problem. And the answer is, well, if we include angles here in this problem, we're really just making the problem a little bit more complicated than it needs to be, because we can always take this lever system and lower the pivot point and reduce the angles, make the angles smaller and smaller and smaller. And so there's really no sense in just throwing some angles in here just to make things complicated, especially when we're just trying to look at a simple example here. But in reality, remember that sometimes there's a sine theta for your torque equation. So force times lever arm times sine theta. Another way to remember it, you go ahead and write that down, what I just said. So sometimes there's a sine theta. But not for this problem. Okay. But there's another way of thinking of it, right? And that's that it's the perpendicular force times the lever arm. So the force times the sine theta just gives you F perpendicular. That's another equation maybe to keep in the back of your mind there. Is as long as you use the force that's perpendicular, you don't have to worry about the sine theta. And oftentimes when you're solving problems, it just comes down to X and Y components. Once you figured out the X and Y components, it's clear which one is the one that gives the torque, right? So you have a force at an angle, but if you break it down into X and Y components, maybe the Y component is perpendicular to the lever arm. And so you just use the Y component when you calculate the torque. Simple as that. Now there's something here that I've done on purpose, okay? There's a mistake on the screen right now. I've given plenty of time for you guys to look at it and copy it down into your notes. I want you to tell me what's the mistake, and I want you to direct message me in chat. I want all 9 of you direct message me in chat so that other people can't see. What is the mistake that's on the screen right now? It's been on the screen for at least, I want to say like a minute to 2 minutes. So everyone has to be involved here. Everybody's got to direct message me. What is the mistake that's been on the screen for the last 2 minutes? Something very, very important. Something very, very important is missing on the screen. Okay, a lot of you have given an answer, but there's still some people missing. I want to make sure everybody has a chance. So even if you're incorrect, it's good to just give an answer because it lets me know that you're thinking about it. You're not getting penalized or anything for a wrong answer here, but it helps me understand where everyone is. I don't think I've heard from Sammy yet. I don't think I've heard from Evelyn yet. I think those are the only two I'm waiting on. Sammy, are you here? Evelyn, are you here? I think only one person got the correct answer here. I'm going to go ahead and let you know now. So I'm going to give you one more hint. It has nothing to do with the signs of this expression here. Remember, I told you that as long as there's a minus sign on one of them, it's fine. I said after that one of them has to be negative because it has to be equal to 0, right? If I add two positive numbers, I'm not going to get 0. So the mistake here, it's a common mistake that students make. So it's really important that you realize it. I didn't write equals 0. That's the mistake. Okay, it's an easy mistake to fall into. And so it's very, very important. Just always constantly be reminding yourself equals 0, equals 0, equals 0, right? Because it seems like something, you're gonna look at that and you're gonna know, oh no, that's not gonna affect me, right? But what's gonna happen is like you're gonna write down an equation and not have an equals sign, like equals 0, so it's not an equation. And you're gonna look at it and you're gonna be like, what the heck do I do with this? Like I can't add anything to the other side, right? It's like, what is this supposed to be equal to? Like, how do I move a term to the other side and solve, right? So it's very important. It sounds like something so trivial, but it will really throw you off, especially if you do it, like you're solving a problem for the quiz or something or the test, right? It's really going to throw you off. Always put equals 0, okay? So give me a thumbs up now. You understand what the mistake is. Give me a thumbs up. Okay. All right, good. So now it's just a matter of, and I hope most of you at this point can solve the problem. We're simply looking to solve for this ratio here. R divided by little r. I think all of you are capable of solving this expression, right? So those of you who worked ahead, you probably already have the answer. But basically what we need to do now is, since I have equals 0 now, I can add a term to the other side. So FPR, so that it cancels on this side. And it shows up on this side. And so we have mg little r equals fp big R. And then I simply divide by fp on both sides and divide by r on both sides. So I'm going to do that in one step. Divide both sides by fp and little r. Let's not make that one look like a subscript. Let me draw it a little bit up. There we go. Okay, so little r cancels on this side, and fp cancels on this side. And what we have finally is big R divided by little r is mg divided by fp. Right? Let's maybe box our answer here in purple. This is called the mechanical advantage. Mechanical advantage. And it tells you something really nice about the lever arm. It tells you that you can lift. Well, it's telling you quite a bit actually, but let's look at the simplest thing here. It tells you that if you apply a small force over a large distance, right, you get a big multiplier of the input force as an output on the other side of the lever, where you have some big force on a small lever arm. Okay, so let's go ahead and highlight over here on the actual figure here exactly what I mean by that. So we can see here, maybe I'll use red so it stands out. We can see here we have a big force over a small distance here in red. Big force over a small distance. But over here in blue, we have a smaller force, but it is exerted over a longer distance. Okay. So blue force gets multiplied Okay, the blue force gets multiplied by this factor called the mechanical advantage. Actually, you can see that from this equation right away. This right here is called the mechanical advantage, big R over little r. If I multiply the force of the person to the other side, you can see that the force that the person exerts is multiplied by the mechanical advantage, and then that multiplication factor times that force equals the weight of the object on the other side. So what that means is that when you're given a mechanical advantage for some lever arm or some pulley system or some what we'd call a machine, and a machine in physics or in engineering is really like any tool you use in a tool shop. So like a wrench, some bolt cutters, any of those would be considered machines in physics language or engineering language. And all of those have what's called a mechanical advantage. And so that's why it's real easy for you to take some bolt cutters. Notice the bolt cutters have really long, let me just get like a really simple picture of like some bolt cutters here. Okay. Here's a real simple pair of bolt cutters. Notice that for bolt cutters, this distance here is big R. This distance here is little r. Right? So there's a mechanical advantage there. That's why you can use like some bolt cutters to actually cut through some thick metal, right? Like a, like a lock or something. You lost the key for a lock. You get some bolt cutters, right? And you can cut the lock, something like that, right? And the reason is because these machines or these tools are designed in such a way to get really, really big mechanical advantage. As a matter of fact, for bolt cutters, it's not even as simple as big R, little r. There's actually some extra stuff going on here in the middle region that we won't really get into too much detail because it starts to get more and more complicated. The problems start to get like actually really complicated. You have to be very careful like how you approach, you go through those. If you happen to switch your major to engineering after this class because you love physics so much, if you were to take a course on statics, which is like your first engineering course that you take as an engineering major, then you would study these kind of machine devices. And you might look at some bolt cutters and calculate a mechanical advantage for that. But bolt cutters will give you a mechanical advantage of like 100, 150, 200, like massive mechanical advantage. So that way, if I, some weak person is like pushing on these, let's get a picture here. So if I push on these bolt cutters like this with a force of 100 newtons on each side, which is reasonable, 100 Newton force is reasonable. That's like 25 pounds of force. So like lifting a 25-pound dumbbell, basically, it's not too hard. I'll get a force over here of 10,000 newtons, right? And so 10,000 newtons, now you're talking, like 250, or sorry, 2,500 pounds of force, right? So it's a ton of force. And that's the kind of force that you need to kind of cut through metal. In addition to that, you'll also notice that bolt cutters are sharp, right? And that's actually something that we'll maybe talk a little bit more about later in this chapter, actually, about shear stress. What shear stress is like forces that are kind of acting kind of in the plane of like a cross-sectional area. So it's like if you stick your hand out and you rub your other hand like along that hand like this, that's a shear force. So it's a force that's along the surface. Those friction forces that you're feeling, those are shear forces. Okay, so the big takeaway here from this example, let me just go ahead and write it out, is you have some sort of input force, and that input force gets multiplied by something that we call the mechanical advantage, and that equals the output force. Now, in your textbook, they don't actually write down an equation like this, I believe, but I think this is a really nice equation just for thinking about how tools work, right? Just a nice, simple equation. This is like F equals ma almost, right? But for tools, it's like, do you have a good tool design or not, right? If I input a force, what's my output force? Do I have a big mechanical advantage? As a matter of fact, in some cases, you could even think of tools which have small mechanical advantage on purpose because you're working with something that's delicate, right? And so you don't want to put a really big force on it. You want to put a really small force on it. Right? Like, for example, maybe if you're working like in the jewelry industry, right? You want to use tools where if you accidentally squeeze, that tool a little bit too hard, you don't get a big force, right? You don't like put a dent in, like the gold ring, or, you crack the diamond or something, right? So there's all kinds of different ways to just get so much out of this equation here. It's like a simple equation, right? It's got a lot of content in it. And of course, engineers are always looking at designs, right? Like, how can I maximize the mechanical advantage, or, get a really small mechanical advantage, right? So there's a lot of content there in that equation. Okay. All right. So I said that we would talk about a problem-solving strategy for these problems. So now that we've done a couple examples, let me go ahead and go through that now. So this is our problem-solving strategy. For static equilibrium. Okay. So the first thing that we want to do is get a picture. If we're not given a picture and we're just kind of given in words kind of what's going on, you got to get a picture like right away, right? So that's step number one, is to get a picture, right? So draw a picture. if you're not given one, right? So if there isn't one, just pretty much always. That's actually like just a general problem solving tip, right? It's like you just always kind of want to have a picture so you can visualize what's going on. Okay, the next thing then, once you have a picture, you should draw another picture, which we call in physics a free body diagram, right? And the free body diagram is like a simplified picture that just has all the relevant forces and maybe even torques if you're given a torque. A lot of times in these problems, you're not given a torque, especially in this class. You might be given a torque like in like a course on statics, like an engineering course. You might be given some torques in the problem. But I think in our class we only have forces. So you're going to want to draw a free body diagram like right away. If they give you a picture, you can just skip step one, right? And you just go straight to drawing that free body diagram. Okay. Next thing, kind of an obvious thing, is choose a coordinate system, right? Choose a coordinate system. We have a lot of vectors in this chapter, and nothing is terribly difficult here for static equilibrium. But if you don't pick a good coordinate system, then you're going to end up, having all kinds of signs floating around. You might choose a coordinate system, you end up with like a bunch of minus signs, so you might be more prone to like missing one of them, right? So choose a good coordinate system and then stick with it. Of course, don't sit there and waste 5 minutes thinking about what's going to be the best coordinate system. As long as you choose one coordinate system and then stick with it, you can get the right answers, right? So don't spend too much time thinking about what's going to be the best coordinate system. It's mostly just about pick a coordinate system that, looks good, and then just stick with it, right? So choose a good coordinate system and then stick with it. For the entire problem. Some of this stuff probably sounds a little bit obvious, right? But in this chapter in particular, there's a lot of algebra. Step 4 here is just to apply those conditions, right? So start applying the conditions. So sum the forces. Usually you want to sum the forces first. So sum the forces, sum the x and y components. And really you want to break it down into components, right? So sum the x and y components of force. And then always set it equal to 0. Over here on the side, let's go ahead and write it down in equation form, right? Okay, step number 5, you probably can guess what it is. Once you sum up the forces, sum up the torques, right? Sum the torques and set equal to 0. And then I'll put a little note here, something I mentioned before. You can take like clockwise or counterclockwise to be positive or negative, but then you have to stick with it, right? So maybe, what did I do before? I did counterclockwise as positive. So if you want to stick with that, that's fine. Counterclockwise, positive, clockwise, negative, and then you have to stick with it. You want to sum the torques and set it equal to 0. And then the last step here, and let me just go ahead and move this down. Nice little bonus of doing stuff in Paint here. Just move it down like that. Last thing, solve for your unknowns now, right? So look at your equations, figure out what you can solve for, right? So solve for unknowns, right? So this is basically like you've set everything up now you got to solve the problem. And that's it. So like 6 steps there. Maybe you could combine 1 and 2 into a single step. It's like 5 steps. But there it is. That's kind of the problem solving strategy for this these kind of problems here. So any questions about that? Is everybody kind of warmed up now? So we've done those first 2 examples, and the next I think you already saw, I kind of showed it. We're going to do another example now, right? So we're going to do lots of examples today. So are we ready for that? Are we still writing? Give you guys some more time to just copy that down. Go ahead and scroll it down for those of you who kind of, you think you know what you're doing here. So just, there's the example right there. We have a nice little figure there. And the question is, how far from the pivot point should child B sit in order to balance the seesaw? So you can go ahead and start working on that if you'd like. Give me a thumbs up if you're done copying down the problem solving strategy. Still a couple people maybe copying that down. No worries. We got plenty of time. Maybe after this 3rd example, we can take our our short break, and then come back and we'll work on some more. Okay, thumbs up if you're done with the problem solving strategy. Just one more check here. Certainly everybody's done with steps 1, 2, and 3, right? Okay, just one more, I'll ask one more time. Are there any questions for me about anything up to this point? I do see a chat actually. It's, okay, so we did get a question here about counterclockwise versus clockwise. So let me just quickly highlight what that means. So counterclockwise means rotation in this direction, and clockwise means rotation in this direction. So clockwise is kind of like how the hands go around the clock, right? And then counterclockwise is the opposite way of that. How can you tell whether a torque is counterclockwise or clockwise? Well, you have to like look at a system like this, and if there's a force over here, right, and this thing kind of like on our next example, we have the seesaw. This force right here is going to make this system rotate in this direction. So that's going to be a clockwise torque. So that I would take that to be negative. If I had a force over here, like this, well then that force would want to rotate this thing. This force would want to rotate this thing in this direction. So I would take that one to be positive. Okay, so it depends. And then if I had perhaps like a force here like this, well then of course that would, again, that would want to rotate this thing counterclockwise, right? A force over here, that would want to rotate it clockwise. So you just have to look at your problem and just think about how the forces, are going to rotate the system. So I'll just leave this example here, like so. So if I push down on this side, that's going to be a clockwise torque. So that would be a negative torque. And you can choose, if you want to, you can choose counterclockwise to be negative and clockwise to be positive. That's totally fine. It's your choice, right? As long as you're consistent. So in one problem, you might say clockwise is negative. You have to make sure every clockwise torque is negative in that problem. And every counterclockwise torque is positive. But in another problem, you might change your mind. You might say, you know what, if I choose clockwise to be negative in this problem, I'm going to have like 4 minus signs. So let me actually make clockwise positive for this problem. So just whenever you do a problem, whenever you write down the sum of the forces, you put like an indicator, this way is positive. Or for the torque, you put, okay, this way is positive. And you're just consistent. You just always reference that coordinate choice that you've made. Okay. Does that answer the question? We're going to go ahead and scroll this down. I'll go ahead and leave it right there since we have those equations over there on the right side. So maybe that helps get you started on this one. And I'll actually add a part to this question here. I think it's pretty clear that there has to be a normal force here. There has to be a normal force here at the pivot point on the seesaw. And so that's the part that I will add to this question. Now notice the normal force goes through the pivot point. Any forces that are at the pivot point cannot exert a torque because the lever arm is 0 if the force is at the pivot point. So this normal force will not exert a torque. So you can totally answer this question here without this normal force. But I'll ask you guys to solve for the normal force in the end. So I'll go ahead and write that in right here. All right, so give me a thumbs up if you've been working on this question. You know kind of what you're doing at this point, and you're just chugging along. Okay, only 3 people. And then give me a thumbs up now if you want me to give you a hint. Okay, nobody wants a hint. Okay. I'll let you guys work on this one for a couple minutes and then I'll kind of go through this one after I give you guys some time to work on it. Is anybody lost? Let me know if anybody is lost. You can give me a thumbs up if you're lost. Or you can like directly message me and say, hey, explain this one. Okay, iPhone is lost. Start with just the torques. Okay, start with this right here. So sum the torques. There are two torques. There's one torque due to child A, and there's one torque due to child B. Okay, so let's revisit the problem-solving strategy here. So we have a picture, so we don't need a picture, but you probably want to copy the picture down into your notes. We want to draw a free body diagram next. So how would we draw the free body diagram for this picture here? Well, the first thing I would do is I'd probably just draw a line. And I would say I have a force here, which is MAG. I have a force here, which maybe it's not as big because it's 25 kilograms, not 30. That's going to be MBG. And then I have this normal force here, which actually the normal force, as you'll see shortly, has to be bigger than both of those. And we know the following distances here, so we should include that in our free body diagram because it's going to help us calculate the torque. This lever arm is 2.5 meters, and this lever arm is X. Okay, so you want to sum the torques. Torque is force times lever arm. Excuse me. So any other questions? How are we doing? Give me a thumbs up if you're making progress on this. Okay, Leanne, Matthew, Irving, Jew, Sammy, are we making progress? Give you guys maybe like another minute to keep working. If you're struggling, that's fine. Just keep trying and keep trying to solve out the equations there. Remember, torque is force times lever arm. Got to think about which way is this thing rotating by each of those forces there to get the sign right for the torque. Honestly, when there's only two forces like this, as long as you get a minus sign on one of them, you're fine. If you get an answer, you can go ahead and put it in the chat as well. Then other people can check their answer. Okay, so maybe like 30 more seconds here, and then I'm going to go through the example. Okay, I'm going to go ahead and go through the example now. Um, can you guys give me a thumbs up? Do you want me to go through it slow? Give me a thumbs up if you want me to go through it slow. Okay, we have at least one person, so I'll try to go slow. I'll try to go slower. Okay, so let's go ahead and make some space here first. I've already drawn out the free body diagram. So remember, a free body diagram is like a simple figure. It's got all the forces involved, right? Maybe one thing I should have added to my free body diagram was a choice of coordinates, right? Something like that. Um, Here's what I'll do. I said counterclockwise was negative and, or excuse me, counterclockwise was positive and clockwise was negative. So we're going to take that direction for the torques to be positive. And we'll go ahead and take our XY coordinates like this, right? We don't have to be really picky on this particular problem. This problem is a very simple example. So only two forces involved here for the torques, a third force if you sum the forces. But here's the idea. So if we have this direction is positive, we're going to sum the torques equals 0. That's going to lead us to the following expression. So MAG, the child on the left side, is going to rotate the system with a positive torque. That's the kid that wants to rotate the system counterclockwise. So that one's going to be positive. MAG times the 2.5 meters there. Let me just call this L for a second. So instead of plugging in the 2.5 meters right away, let me write down an expression first. So this L is 2.5 meters. Okay, so that's force times lever arm. And then the child B is going to rotate the system clockwise when she sits on the seesaw, or she's going to, that her force is going to want to rotate the system clockwise, right? So for that case, we have a minus sign because we're saying clockwise is minus. So minus MBG. I see some chats. Let me address real quick. Okay, yeah. Okay, so MBG for her force, her weight, times the lever arm. And the lever arm here is, I'll do it in blue again, X. Okay? We always, always, always remember to set the summation equal to 0. Always set the sum equal to 0. So now we have like a little expression here. Of course, everything in the expression is known except for x. So let's solve it for x first before we plug in any numbers. A nice thing that you probably noticed is that g's cancel here. We have a g on every term on the left side and a 0 on the right side. So we can actually cancel the g's here. Let's cancel out the g's, divide both sides by g. So we cancel g on the left side and we're just dividing 0 by g, so it's gone. That leaves us with MAL minus MBX. And we can solve this thing for x. If I add MBX to the other side, I add it on both sides, I can do this little trick where I just say MAL is equal to MBX, right? You can just get rid of the equal 0 because I add MBX to the other side. And then to solve for x here, we simply divide by MB. So we get that x is equal to MA over MB times L, like that. And now we're ready to plug in numbers, right? Because we have MA, we have MB, and we know what L is. Maybe we'll use purple here. So MA is 30 kilograms. I'm going to leave off the units here. I think the numbers work out nice and easy. So 30 divided by 25 times 2.5. You can see here 2.5 divided by 25, that's like a tenth, right? We get this, and this becomes a 10. So we end up with 3. meters for x. So if these two children want to balance on the seesaw, the girl who is less massive than the boy has to sit a little bit further from the pivot point so that the torques balance out. And if you have any experience with seesaws on the playground, oftentimes you can't really move the pivot point, right? So if like there's a big kid on the other side and you're on your side, the big kid's on the other side, and usually you're always like up in the air, right? But in the old days, when the kids were outside with the big long sticks and a rock, you could move the fulcrum point around, or the pivot point. That's another name for the pivot point, is the fulcrum. I can write that down. So fulcrum. That's the same as pivot. Pivot point. Yeah, so there you go. There's 3 meters, and that will balance the torques. Now I did add a second part there to that question. Let me see if I have some space I can scroll down. I think we have a little bit of space here. Yeah, we do. We have a little bit of space. Let me go ahead and drag this example down. This is a little bit more of a complicated example, but I think it's actually a really good It's actually a really good example that helps explain a lot of the stress that goes on in your body, like muscular stress, skeletal stress. It's very counterintuitive. Okay, so we want to get the normal force here in this problem. This is a part that I added. Okay. So does anybody have an answer for the normal force? Did anybody actually get to solve that? Go ahead and let me know. Okay, so somebody did. Christine has an answer. 580 newtons. Anybody else? Okay, maybe nobody else got this one. This one is pretty straightforward. We sum the forces, but there are only forces in the y component, right? So we'll take up to be positive, excuse me, and we'll sum the y components, set it equal to 0. We have three forces here. We have the normal force, which is up, so that's positive. And we have the two weights, and those are both down. So MAG, MBG. And somebody tell me in chat, what do I need to do now? What's the next step? I've summed the forces. What do I need to do? Okay, good. So a couple of us paying attention. Equals 0, right? Equals 0. Always remember that equals 0. I have a feeling no matter how many times I remind everyone, somebody at some point is going to forget to put equals 0. But okay. So now we solve for the normal force, right? So we can move the other terms over to the other side. So the normal force is equal to MA plus MB times G, just factoring out the G there. Nothing new here. We're used to seeing stuff like this, normal force related to weights, right? We can go ahead and plug in our numbers. This one maybe I do need a calculator for, I'm not sure. So 30 plus 25 times G, which is 9.8. Leaving the units off here, we know this is a force that's going to have units of newtons. So this is 55 times roughly 10. 55 times roughly 10, so I would say 550 newtons roughly. Roughly 550 newtons, a little bit less than 550 newtons. So I'm wondering, Christine, maybe check your work there. 580 seems a little bit too big. I'm wondering like how you got 580. Okay, so you did end up 539. Okay. So it comes out to 539 then. All right. That sounds about right. So we'll take that as our answer, 539 newtons. Any questions about that there? Any questions?
I don't know if this is thinking too far, but if this is a problem that we have and they give us like the weight of the seesaw, we have to account that into the normal force, right? It doesn't just like,
Yes.
okay.
Yep.
Okay, thanks.
Yeah, and that's a good point. The weight of any object will act at its center of mass. So in this particular problem, if this is a uniform seesaw, then the weight of the seesaw will exert a torque about the pivot point. So that's actually a very, very good question. So the question is basically, and I think I'll have to kind of like maybe clean some stuff up over here. Go ahead and clean this up. think we can just delete that as well. So since x is 3 meters, then the seesaw is not, it doesn't have its pivot point at the center of mass. So the center of mass of the seesaw is probably somewhere right there, at the midpoint of the seesaw. So if the seesaw is 5.5 meters, then that means that the center of mass is 2.75 meters from this kid right here. So this distance right here would be 2.75 meters. And the weight of the seesaw here acts, so let's say mass of the seesaw times gravity. So that the weight of the seesaw acts at its center of mass. And so that's just right in the middle of the seesaw, the plank, right? The wooden plank or whatever it happens to be. And you guys, I think you all can see now that the seesaw's weight exerts a torque on this system, right? The seesaw's weight exerts a torque on this system. And how much torque would that be? The torque due to the seesaw, if we remember that we're taking clockwise rotation to be negative, so we could put a minus sign here. That is what I chose, right? Clockwise is negative, yeah. So the torque due to the seesaw's weight is negative mass of the seesaw times the gravitational, so it's its weight basically, times the distance it is away from the pivot point. If this distance to the center of mass from this kid here is 2.75, and the distance from the kid to the pivot point is 2.5, then the distance from the center of mass of the seesaw to the pivot point is 0.25 meters, like a quarter of a meter. So it's a small lever arm, but we definitely would have to account for that in our calculations. Okay, so actually that brings me to a question for everyone. It's kind of a conceptual question. If we were to account for the mass, the weight of the seesaw, would x be bigger or smaller? So that's a question for you guys. I'll type that one out in the chat. So if we account for the weight of the seesaw, would x be bigger or smaller? So would the child have to sit closer or further away? So question for you guys. Give me a thumbs up if the question makes sense, like you understand what I'm asking. Seeing a couple answers. It's good. I like to see a lot of answers. This is finally we have some engagement in this class. Okay, so has everybody had a chance to answer? Not quite. Maybe a couple more of you want to give some input, and I'll give like maybe another 30 seconds there to think about that. Feel free to change your answer. If you think about it, you want to change your answer, go ahead and change your answer too. Looks like one person's already changed their answer. So if we account for the weight of the seesaw, should child B sit closer or further away? So should X be smaller or should X be bigger? I love how much disagreement we have in the chat. This is always good whenever we have disagreement. So it makes people think more. So it's like, am I wrong? Did I make a mistake or something? Right? So you got to think a little bit more about it. So let's go ahead and answer the question now. Okay, so follow along with the logic here. I'm going to clean up a little bit of space here. So we need to remember our answer from before, 3 meters, right? So I'm going to delete that now. And let's add some space here to this equation. I'll give you guys some time here to copy down the equation I'm about to write. So MAG times L, which is our 2.5 meters, minus MBG times X. And we said we would now have an extra torque here in our problem. And it's a clockwise torque, so it's negative. So minus M, mass of the seesaw, times G. And then times this 0.25. Let's give it a name. Let's say maybe it's this is like, let's say LA, and let's call this one LS for the lever arm of the seesaw's center of mass. Okay, which is our 0.25 meters there. But let's just get an answer analytically before we really can't plug in numbers because I didn't give a mass for the seesaw, right? But we could at the end. We'll go ahead and give it some mass and we'll see what happens. Okay, so if that's the case, G's still cancel. Notice there's a G in every term still, so G's will still cancel. And we want to isolate X. So let's write this thing out one more time. So M-A-L-A minus MSLS. And we'll put MB times X on the left side. So I'm adding MBX to the other side. So I take this equation here and I add MBX to both sides. Add MBX to both sides. And what I have is MBX equals MALA minus MSLS. Okay. Now divide by MB. And we have an expression for X. But hopefully some of you already notice that it's impossible for X to be bigger, because this was our answer for X before, and now we have minus MS over MB times LS. And we're subtracting a positive number from the answer that we had before. So what we could do is we could say, let's go back. Now that we've established, now that we're solving for X when the seesaw has mass, Go back to the beginning of our equation. Let's put like an x prime here. Put an x prime instead of just x, because this is a different x, right? So it makes sense. Let's put an x prime, because then that allows us to identify this piece here as our old x. So this is our old x with no prime, just x. So we end up with x prime, the location of the new, where child B should sit now, if we account for the mass of the seesaw. Where's my mouse at? There it is. It should be shifted, and it should be shifted to the left because we have subtraction here. So this is the amount that x changes due to the mass, or due to the weight of the seesaw. So does that make sense? Does the math now show that that child could now sit closer? Does everybody agree that x is going to be smaller now? Since the mass, or rather the weight of the seesaw, if you look at the figure up here on the top right, notice that that weight is to the right side of the pivot point. It's to the right side of the pivot point because the center of mass of that rod, or of that, the center of mass of the seesaw is now going to be on the right side, because we know that the smaller mass child has to sit further away from the pivot point. Okay? So we know that that child will be able to sit a little bit closer if the seesaw has a weight. Of course, it's always going to have a weight, but maybe this is a small weight, right? Maybe ms, maybe ms times ls here is small compared to the mass of the child B, right? So if this ratio here is small, then there's not much shift, right? And so the x that we had before is approximately the right x. But if we want to account for that mass, then we could get this exact expression here. Okay. All right. So let's go ahead now, and if there are no questions, so let's open up the floor to any questions. Are there any questions about that? Do we have any questions? Okay, so it seems like we're good. So we'll go ahead and move on to quite an interesting example. It's maybe a little bit of a challenging example, but it's I think we'll all find this example to be quite interesting. Especially this class, usually a lot of the students in this class are interested in biology or like pre-med, that kind of pathway. So here we have some forces that muscles are exerting on tendons and bones. in order to lift a ball in our hand, right? And so after this example, we'll be able to appreciate how strong our muscles actually are. Um, Even if you're fairly weak, like as a person, like you can't really lift like heavy weights, your muscles are really putting in a lot of work and generating some really big forces for you to be able to lift certain objects. Okay, so let's go ahead and read the example here. Example 9.8 in the book. By the way, the book has a lot of good examples, including some of the previous examples we did. I just kind of took the figure and then just kind of simplified the problem a little bit. This particular example I decided to copy just verbatim because it's a really good one. So the force exerted by bicep muscles, or biceps muscle, how much force must the biceps muscle exert when a 5 kilogram ball is held in the hand in figure A with the arm horizontal, as in this figure over here. So let me draw an arrow, so this one. And B, when the arm is at a 45-degree angle, as in this figure, right? The biceps muscle is connected to the forearm by a tendon attached 5 centimeters from the elbow joint. Assume that the mass of forearm and hand together is 2 kilograms, and their center of gravity is as shown. That's what they mean by CG. So same thing as center of mass, okay? Same thing as center of mass. So CG, center of gravity, center of mass, same thing. So how do we start with a problem like this? Well, we just apply our problem solving strategy. So the first thing is to get a picture if you don't already have one. Thankfully, we have one for this problem. The next thing to do is to draw a free body diagram, right? So that's what I want you guys to do. Just draw, don't solve the problem fully. We'll go through this one together. This is a little bit more of a complex example. A lot more going on in this example than previous examples. So just draw a free body diagram for figure A here. Just a free body diagram here for figure A. Free body diagram for figure A. I would start by simplifying this thing greatly by assuming that we just have this rod here, just a thin rod. That's basically the forearm. So approximate the forearm and the hand together as just this flat, seesaw basically. So start with that, and then you can start adding in some forces to that. One of the important things, actually, maybe I didn't emphasize this on the last example, is when you draw a free body diagram, really make sure that you label the distances that you're going to use for your lever arm. Okay, really label those distances. And then I'll talk in a minute about how we're going to sum the forces and the torques for this problem. Summing the forces is not hard. That's just write down the summation. Everything is in the y direction. But summing the torques here, we want to make sure we have the point at which we're calculating the torque. We select that point so that we don't have to worry about one of the forces. So I'll talk more about that in a little bit. Let me know if you're done in the chat with drawing the free body diagram. Let me know in the chat if you're done drawing the free body diagram. Okay, I see some of you are finished now. Okay, good number of you are finished, so I'll go ahead and finish it off here. So the free body diagram should look something like this. And then at the distance here of 5 centimeters, then we have this force here, which is basically mg. And this is at a distance 15 centimeters. And getting these distances in here is very helpful. And you're probably better at drawing this than I am on Paint, because you can actually like maybe write small and write the distances closer, so it's a little bit easier to see. And then finally this one over here, it's another mg basically. This is 5 kilograms. This one is 2 kilograms. And this distance here is 35 centimeters. Okay. So now that we have the free body diagram, we can go about answering the question. So those of you who know what you're doing, you feel free to work ahead as much as you would like. We want to know the force, or how much force the biceps muscle exert when a 5 kilogram ball is held in the hand, in part A with the arm horizontal, okay, which is what we've drawn for this free body diagram here. So how do we go about doing that? Well, there are two forces due to weights that are giving us torques in this direction, which is the clockwise direction. And the clockwise direction is negative. Well, just based on what we said earlier, but of course you could choose that to be positive if you want. And then there's one torque due to the muscle, the biceps muscle, due to the force Fm, that is going to exert a torque which would be in the opposite direction. In other words, the counterclockwise direction. So we can take that one to be positive. Now, this assumes that we're calculating the torque about the point of which the system will rotate, which is at the joint. And so since we're calculating the torque about the joint, the force on the joint will not have a torque associated with it because the lever arm will be 0. Okay. So when we sum the torques, we're summing the torques at the joint. That should be equal to 0. Now, what are the torques that we have in this problem? Well, we have the two torques that are clockwise, which are going to be negative. Those are going to be minus 5 kilograms times g, and minus 2 kilograms, minus 5 kilograms times g times the lever arm, which is 35 centimeters. Okay. You could convert this to meters. You could say 0.35 here. That's fine. Since all of the distances here are given in terms of centimeters, it's okay if you use centimeters. That's not going to cause any problems. If some of these were given as centimeters and some were given as meters, then you'd have a problem. Since they're all centimeters, I'm just going to use centimeters. So minus 5 kilograms times g, that's the weight, times the lever arm, which is the 35 centimeters, minus the 2 kilograms times g times the 15 centimeter lever arm, right? And then we have the muscular force Fm, which is positive. So Fm, just take the magnitude times the lever arm of 5 centimeters, and then set that equal to 0. Let's go ahead and consolidate a lot of these numbers here. So we're going to have minus 5 times 35, that's 165, or excuse me, 175. Times g. Notice that g is not going to cancel out here in this problem because there's no g on the third term. And also remember, like I said, that the force on the joint has no torque. So there's only three terms here. A couple things to keep in the back of your mind there. So for the second term, 2 times 15, 30, right? And then finally, 5 Fm. Just reorganizing the equation so it looks a little bit nicer here. Then we can rearrange the equation so we can add the negative terms to the other side, and what we get is 5 Fm is equal to 205 G. So 205 G equals 5 Fm, divide by 5. We get that the magnitude of the force exerted by the bicep is 41 times, well, I mean, this is already enormous, right? So 41 times G, which is equal to 41 times 9.8, approximately 410, right? You could subtract off, it's like, I think it's going to be like 408 or something, 400 and something like that, I don't know, 408. Does anybody have the answer? I can just punch it in on the calculator. Oh, 418 is it? 418. No, it can't be. It can't be 418. It's gotta be less. Yeah, there we go. 408. That makes sense. That makes sense. So 408 newtons. Something like that. While you guys are copying that and catching up, I can just punch it in the calculator over here. Oh no, not 408 actually. 402.8 I get. So we round to 403. Round to 403 there. Okay, so any questions about that part? So simply lifting a 5 kilogram ball. Let's get the weight of the 5 kilogram ball so we have a sense of what to compare to. 5 kilograms times 9.8 meters per second squared. This comes out to 49 newtons. So this is the weight of the object. This is the weight of the object, and this is the force of the muscle. So you probably weren't expecting that heading into this example, but this is the reality of the situation. That lifting even the lightest objects, with your muscles, requires a lot of force from your actual muscles. So despite the weight of the object not being that much, because the lever arms are so large, like for your arm or like your shoulder, if you're lifting with your shoulder, right? That's why it's so difficult actually, like to lift a weight all the way out with your arm fully extended about your shoulder like this, is because the lever arm is so large that the shoulder muscle can't support such a large amount of torque on your shoulder. So the force of the muscle is about 10 times as much the weight of the object you're trying to lift. So hopefully that gives you more of an appreciation of how hard your muscles are working. Any questions about that? Or give me a thumbs up if we're ready to go to part B. So Leanne, Matthew, Irving, Sammy, how are we doing? Okay. And maybe one of you is okay. Um, okay, so it looks confusing. My brain just needs more practice to process. Which part in particular is the most confusing? Okay, so let's get a little bit of space here. So now we're looking at part B. So I'd like to ask you guys again, go ahead and draw a free body diagram for part B. Yeah, Leanne, it helps if you kind of, it helps if you like do every problem, like start the problem exactly the same way and just kind of, um, like if you recognize it's a static equilibrium problem, then you just kind of remember that you have to write down a summation for the torques, write down a summation for the forces. And so, yeah, it is kind of like getting more practice, but maybe it would help if you had, maybe you have like a separate sheet of paper with the steps written down on it. And then like you have that sheet of paper like next to your notes. So that way, when you come to a new example, you can just reference that sheet. And then maybe after several examples, you don't have to reference the sheet anymore. So free body diagram for part B. Here's what we'll do for this next one. Once we finish the free body diagram, I'll put you guys into the breakout room so you can work in like maybe groups of 3 or something. And then I can just come around and visit each group for this next part. And by the way, just if it's not clear from the picture that we have here, um, some of those forces are the same, right? The weight of the ball is still the same. The weight of the forearm and the hand is still the same. So these forces right here are still the same. In the top right figure there, where my arrows are, those forces are the same. But this force here, the force from the bicep muscle, that one's going to be different now, right? I think we all know it's a little bit easier when the weight is kind of hanging lower, and then it becomes it's the most hard. So if you watch my arm here, right, like I don't know, maybe I should like stand up or something, but like if your arm is like this, that's the most hard, or sorry, that's the hardest, the most hard. That's the hardest. And it's a little bit easier to lift the weight when it's like around this range, right? A little bit easier. But once it gets to here, that's the hardest. And then once you get it up over that point, then it's a little bit easier again. A little bit easier to lift the weight. So down here, it's kind of easy. Up here, it's kind of easy. But getting past this point is really where it gets hard, right? When your arm is at a right angle. I'll give you guys maybe like another minute there to finish off the free body diagram. This one's a little bit different than the other one because like some of the forces are the same, but then the force of the muscle is different. But what really changes here drastically are the distances, right? Because of the angle. So um, that's the really important part here for this one. The distance along the arm doesn't change, right? But the lever arms change. Go ahead and tell me you're done in the chat if you've finished, so I know I've given you guys enough time. I see a couple of you messaging me. That's maybe only like half of you though, so maybe I'll give a little bit more time. I'm just answering some questions from students in my other class via email. Let's see, how many do we have done now? So 1, 2, 3, 4, 5, 6, 7. A couple more of you. 8. Okay, we're almost there. Haven't heard from, it looks like Irving and Kevin. Another 30 seconds here. Okay. Oh yeah, you did actually say done, Kevin. So Irving, are you good on this one? You need to see me do it. Okay. Let's go ahead and go over it now. I don't want to spend too much time here. Keep everyone waiting. Um, the free body diagram looks like this. We have the force on the joint. We have the force, the bicep. We have the force at the center of gravity of the arm and hand, and then of course we have the force on the the weight of the ball that we're lifting. So there's this one, there's this one. An interesting thing for you guys to do, maybe on your own, is to come back to this problem when we're done here and calculate the force on the joint, right? Because that's also an important force. So you understand like how much force there actually is on your joints when you lift objects. This one was the mass of the ball. This one was like 2g, and this one was 5g here. 5 kilograms times g and 2 kilograms times g. Okay, so our lever arms have changed here, but the same principle applies. We sum up the torques, and we can take, what direction did I take positive again? Counterclockwise. So counterclockwise was the positive direction. So that would be the force on the muscle there. That's going to be the positive torque, and we always want to set our sum equal to 0. So what does this lead to? Let's go ahead and switch back to black now. So the positive torque is going to be Fm magnitude times the lever arm. Okay, well now things get a little bit tricky. So this lever arm distance here, now that the angle is 45 degrees, well, we can draw out a little triangle real quick. This is 5 centimeters. This angle here is 45 degrees. Okay, and so 5 times the cosine of that 45 degree angle will give us the perpendicular lever arm. Excuse me. So 5 times cosine 45, so cosine 45 is root 2 over 2, right? Or 1 over root 2. So that's going to be, let's go ahead and move that out of the way too. So take this and we'll move it down here. So we have some space to finish off our equation. So Fm times the lever arm, 5 cosine 45, pi over 4 if your calculator is in radians, right? Subtract from that the negative torques, which are clockwise. it's going to be 5 times g times the lever arm. And the lever arm, if I remember right, this was 15 centimeters. Yes, it was 15 centimeters. So 15 times cosine 45. And all I have to do to understand that it's the cosine is I just come down here to my picture I already made. And instead of 5, I just put a 1 there, right? The triangle is the same. It's the same angle there. So it'll be 15 cosine 45. And then we'll subtract from that the 2g, and this one is 35 centimeters away, but again, it's 35 cosine 45. Okay, and then I have to slide on over here
Yes, sir.
so I can write equals 0. Yes.
I don't know if I'm tired, but can you scroll up to your previous diagram? Did you switch the 5 and the 2 masses?
Oh yeah, I did actually.
Okay.
Yeah.
Okay, thank you.
Yeah, so let's fix that up. So thanks for that. Get rid of the 5, get rid of the 2, swap them around. So this one is 2 and this one is 5. Okay. There we go. So equals 0, and then we can go about solving for FM again, right? All of these cosine 45s are like 1 over root 2. I think your math teachers always get mad whenever you write a radical in the denominator. But if you if you actually take some math classes, usually you get a little higher up and nobody cares anymore. Okay, so and the nice thing is that there's a cosine 45 on all of these terms here. So we can cancel all of these out. This seems something seems off here actually, that we can cancel all of these cosines. No, I think it's good. So if that's the case, if we cancel off all these cosines, then we end up with the same answer as before. So it's going to end up being, what was the answer we got before? 403 newtons. Let me just double check in the book here on this one, because I am a little bit skeptical, but I think it's correct. There could just be some simplifications being made in the problem. Let's see here. Yeah, so okay, this is for this particular problem, the force on the muscle is the same. Okay, so probably there's a small simplification on what's going on here in the actual arm. So probably a couple things maybe to notice is that we're not taking into consideration the muscle of the forearm muscle, which is gripping the ball, which would also exert a force. Let's see if maybe we can draw it in here. So the forearm, which would exert a force in this direction. To pull the fingers in, right? So there's maybe a couple different things here that could be going on that maybe because I think we all understand that when you're lifting weights, like as soon as it becomes a right angle, that's the toughest part, right? That's why most people are able to move the weights a little bit before, like when they're lifting heavy weights, before they realize it's too heavy. So there's a little bit of simplification going on here in this problem for sure. But for what we have uh, presented to us, we have the correct answer. So any questions about that? Okay. No questions. So we'll go ahead and go on to one. Let's go ahead and do one more example since we have this extra time here. This is pretty much everything I wanted to cover for today because this is like everything that static equilibrium is all about. And I wanted to just make sure we covered all of static equilibrium. And then in the next part, we would cover um, like elasticity and fracture. And so this is the chapter where they actually mention Hooke's law. Um, not any of those previous chapters, but I know I went over it a little bit with you guys. But yeah, so that's the whole plan, was to just break it down into two parts. So we'll go over elasticity and fracture next time. You guys should be pretty well equipped to handle like the pre-lectures, tutorials and stuff for this chapter. So we'll do let's do one more example since we have the extra time here. And actually the book gives another nice example. Might as well just go over it since it's got a nice figure. It's always hard to find problems with nice figures. So whenever you have some problems with nice figures, you always want to take advantage of that. So here's what I'll do. I will print screen and then do something like this here. And I will come in and grab this figure right here. And I'll just go down here. And we'll just paste it right here. Oh, whoops. My mouse is giving me trouble. There we go. And maybe we can enlarge it. I think it gets a little bit blurry if we enlarge it too much. Maybe that helps you see it a little bit better, but it's not too blurry. And then we can go ahead and grab the text of the problem as well. And this is the problem statement right here, nice and simple. Oh, whoops. Can enlarge it a little bit, but yeah, it gets a little bit blurry if we do that, so maybe not. Okay, so there it is. There is the example, forces on your back. So this is a model of like your spine as a rigid rod here. And we're looking at a bunch of different weights on the back and forces due to the muscles on your back. And so we'll go ahead and get some numbers here for this problem. And they give WH is the weight of your head, which they take to be roughly 7% of your overall weight. the weight of your arms is about 12% of your body weight. And the weight of what they're calling the trunk is basically like your torso, is WT. Actually, they use a capital T here, so I want to make sure that the subscripts are right there. They take to be about 46% of your overall weight. Okay, so we have the weights here that are involved. We have also two other forces, Fm, that's the force, and let me see if I get this right here. This is the force, where's the name of the muscle here? Maybe they don't actually give the name of the muscle. So some muscle in your back there. It's in this figure here, erector spinae muscles. So that's this force right here, this one, Fm. So I can type that out for you guys. Can I zoom in on the figure a little bit more? Yeah, I can. It's going to be blurry though, so I can zoom in on it, or I can kind of blow it up a little bit. Either way, it's going to get a little bit more blurry. So let me go ahead and just do this. Does that help a little bit, or is it getting too blurry? Okay. And then Fv is the force on the lumbar vertebrae. Spell this right. So specifically the fifth lumbar vertebra. And that's what we want to solve for. If I remember correctly, calculate the magnitude and direction of the force Fv acting on the fifth lumbar vertebra as presented in the figure. Okay. In this particular problem, we will highlight a concept which helps us solve problems like this when you have a lot of forces involved. And that is that in order for the condition of static equilibrium to hold, namely this one, the sum of all of the torques equal to 0, this must be true at any point. Okay, so this has to be true at any point. It's not just true at the pivot point, wherever the thing is going to rotate about. It has to be true at any point. Now, remember before, if we calculated a torque, it could be different depending on what point we chose. As soon as the sum of all of the torques is 0, then that's going to be true at any point, okay, when we have static equilibrium. All right, so there's a nice point that we should choose if we're solving for Fv here. Fv acts at the kind of the point S down here, this point right here. That's the force we want to solve for. So if we were to calculate the torques about that point, we would not have an equation that had Fv in it. If we were to calculate the torques about this point here, then that force might show up in the equation. Now, in this particular case, this force is, I believe this force is parallel to the spine. Let me double check that. It would not factor in. Yeah, I believe this force is supposed to be parallel to the spine here. So this force would not factor in to our equation for the torque because it is along the line of the spine here. So there's no torque, there's no perpendicular distance between that force and that point. However, this point, the black point that I've labeled there, is a really nice point to calculate the torque about, because two of the forces, or excuse me, actually three of the forces will not be exerting a torque about that point. The lever arm distance will be 0. Okay, so the weight of the head and the weight of the trunk. No, actually, this force FV must be making an angle with respect to the spine here. Otherwise, this system wouldn't actually make any sense. So I'm wondering, what did they write for that? Okay, so what point are they taking the torque about? Okay, they do take the point, they do use the point S to calculate the torque, but they're solving for FM to start, which that's fine. You can do that. That's fine. I wonder though if there's a better way to solve this problem than what they've chosen here. But we can just follow their method. Let's not change too much here. So we'll do this about the point S. So we'll sum the torques about the point S, and we'll just see what happens here. So we'll sum the torques about the point S. There's going to be, let's count up the number of torques here. If we're doing things about the point S, this force here, Fm, contributes a torque. It's in the counterclockwise direction. Counterclockwise, I believe, is, I chose to be negative, right? No, counterclockwise I chose to be positive. So let's go ahead and write that in. Positive. Does everybody see that this force Fm would give rise to a counterclockwise torque? It's wanting to rotate that person's spine back towards the vertical direction, so that would be counterclockwise. And the three weights here, WT, WA, and WH, would want to rotate the spine downward, right? That's going to end up being clockwise. Okay, so the force times lever arm for Fm, so Fm times the lever arm. In this case, we're given an angle of 12 degrees for Fm with respect to the spine. So if that's the case, we need just the perpendicular component of Fm in order to calculate the torque. So notice that the side, let's go ahead and draw a figure here. So this is the spine and the force. So this is Fm, this is the spine here. The force that is perpendicular to the spine is this component here. If this is 12 degrees, then this component here would be Fm times sine of 12 degrees, right? So Fm times the sine of 12 degrees. That's the perpendicular component of the force. And that force acts at the black point, which is 48 centimeters away from the blue point. So times 48. And we can leave that as centimeters. That's okay, because everything in the problem is given in terms of centimeters. Now, the next torque, maybe we want to subtract because it's clockwise. That would be the torque due to, let's say, WT. WT is 0.46 times the weight of the person, the overall weight of the person. That force is directly downward, and so we need to find the perpendicular, the component that's perpendicular to the lever arm, or we can find the perpendicular distance from the force WT to the blue point. So there's two options there. Let me go ahead and draw out what I mean. So if this is WT, we could figure out this component right here. This would be the perpendicular component. And then we would use the lever arm of WT has a lever arm of 36. The WT perpendicular has a lever arm of 36 centimeters. I think actually a better way to think of it is because they've given us this 30-degree angle right here in blue, that we could take WT times this distance right here, and this distance right here is 36 times cosine of 30 degrees. Right, so, and by the way, this was WT, maybe WT here, and this is WT perpendicular, that component there, this component here. So I think that's a little bit of a better way of thinking of it. So we have the force WT, and then what's the perpendicular distance between that force and the point that we're calculating the torque. So that's 36 times cosine of 30 degrees. Cosine of 30 is 1 over root 2. Or excuse me, sorry, it's root 3 over 2. Subtract off now the torque due to WA. So WA, the weight of the arms, 12% of the body weight, so 0.12 times W. And then it's the same thing again for the lever arm, except it's 48 centimeters times cosine 30. So times 48 cosine 30. And then we have one last force here. So minus the weight of the head, which is about 7% of the overall body weight, times 36 plus 12 is 48, plus 24 is 72, times cosine of 30 degrees again. Same argument there. So it's the perpendicular distance to the blue point, the point S. Okay, and then the last thing I have to do whenever I start writing down the summation of forces, I should always put equals 0, right? And now everything here except for Fm, we're assuming is a known quantity. So we can crunch the numbers on this. And what we end up with is that Fm is going to be some number times W, right? Because W we're going to assume we know what W is, but we're not given a number for W. So this force is going to have, it's going to be given in terms of a ratio or some number times the weight of a person. And most likely that number is going to be a number bigger than 1. That's my suspicion. I suspect that number is going to be bigger than 1, right? Because we all know we're not supposed to lift stuff up with our backs, right? We're supposed to keep our backs straight and use our legs to lift things. So I suspect that that number is going to be bigger than 1. Let me go ahead and add in some steps here so we really can see how we should plug this into the calculator. So we got to add these terms to the other side, right? So add these terms to the other side so that we have this thing equals, I'll get rid of the 0 because I'm adding those terms to the other side. And I'm going to pull the W all the way out in front. Okay, so we have 0.46 times 36 cosine 30 degrees. Excuse me. So 36 cosine 30. Oh, whoops, no, that should be a small parentheses. And then plus 0. And the cosine 30 is also the same on these 3 terms, right? So let's go ahead and factor that out as well so we can save some writing. So times 36. And actually, I can pull it all the way out here with the W. So we'll go ahead and do that. So there's a factor cosine 30 degrees I'm pulling all the way out of everything. So plus 0.12. And this is all algebra here, so if you need to take your time with this, just go as slow as you need to. All I'm doing here is solving this for FM. Okay, that's all I'm doing here. 0.12 times 48. And then plus 0.07 times 72. Close the parentheses off now. So it's the weight times cosine of 30 degrees times this stuff in the parentheses. But notice we also have this sine of 12 degrees and this 48 here. So we need to also divide this thing by that. So divided by 48 times sine of 12 degrees. And so now we can punch this thing into our calculator, right? Just leave the W off on the side and then calculate the rest of this number. And we have our answer. So I'll go ahead and use Wolfram Alpha over here. Times, making sure I put parentheses where I need them. Always make sure you got your parentheses right in your calculator. You guys can calculate along with me if you have a calculator with you. Okay, and indeed we get a number bigger than 1, so kind of makes sense. I ultimately end up with approximately 2.374 times W. So FM, so 2.73, and I think this is actually an exact answer. I think the two, unless Wolfram Alpha is playing a trick on me here, it's telling me this is the result right here, 2.374 times the weight. So it's like more than double your weight. the force that your muscle is exerting on your back. So that's why back injuries can be caused when you try to lift things with your back, right? And this doesn't account for this force here. There's also this force FV, which is like a force that's compressing your vertebrae. So that's going to compress all of your vertebrae. We could solve for that force as well if we want to. Actually, that is the problem actually here, is to solve for that force, not this Fm. So now what do we do if we want to solve for that force? Well, we know the magnitude of Fm. So now we can just start summing up all the forces. We have to set all the forces equal to 0 now, right? So if there's any questions there for that part. We can finish this problem off before I end the recording and the meeting. So are there any questions for that? Or give me a thumbs up if we should move forward. Slide over like this maybe. Kind of keep some of the information there. So what we need to do now is we need to sum x components and sum y components. And whenever we sum, we set them equal to 0. And we'll take to the right to be positive, we'll take up to be positive in those cases there. Let's go ahead and divide our work here. Okay, so let's go ahead and sum forces in the y direction first, I guess. We have these 3 weights here, which are all in the y direction, the negative y direction. And we have also Fm, as a matter of fact, has a negative y component. It's maybe not all that obvious, but there, if you draw, excuse me, excuse me, if you draw the horizontal line there, then it becomes a little bit more obvious that it's negative. So the question is then, what is this angle? Right, what would that angle be? Well, in order to figure out what that angle is, you have to use the other angle that we were given in the problem from this triangle right here. I'll do this over here in the corner. So this angle was 60. This is a right angle, so this one must be 30 right here, right? If this one here is 30, then that means not this one. This one's not 30, but this one is 30. Okay, so be careful with your triangles, right? Always be careful with your triangles. So this one is 30. So if we subtract 12 from 30, we get the correct angle. So it's 18. Okay, so this angle here is going to be 18 degrees. So sine times that guy will give us the y component, and cosine times that guy will give us the x component. Okay. So let's go ahead and sum in the y direction first. So we're doing y. Okay, maybe I should just not write anything extra there. So let's just write it. Or I can still stay on blue here. So it's going to be minus weight of the trunk minus weight of the arms and minus weight of the head. Those are all down, so they're negative. And then we have minus um, FM times sine of 18 degrees. And this is something that's known to us. We know FM in terms of the weight, which is right here at the bottom left. And then we have FV. And FV, if it's parallel along the spine, it's at a 30-degree angle. So if we want its y component, it will be FV sine 30. And that is the only positive force in the positive direction here. So you can probably suspect that FV is going to be a pretty big force, right? Because basically all of these forces are adding up to get us FV here. So this is the one that's going to be the really big force. This is probably the force that injures your back here. So FV times sine of 30. And then I ran out of room here, so I got to make sure I put equals 0. So I have to scroll on over. Equals 0. Okay. There's our y components. Let's do x now. So for x, we have two forces only. We have Fm and we have Fv. So those are going to have to be equal to each other, but we'll take to the right to be positive x, so that's going to be Fv times cosine of 30 degrees minus Fm times, and remember it's that 18-degree angle, so times cosine of 18 degrees. And that has to be equal to 0. So we can get the magnitude of Fv right away from the second equation there. So actually, probably we don't even need to sum the forces in the y direction. Since we know Fm, we know the magnitude Fm, we can find the magnitude of Fv straight from the second equation there. So that's nice. So we don't actually have to solve the first equation. So that can happen sometimes. Don't expect that to always happen though. So Fv will be equal to Fm cosine 18 degrees divided by cosine 30 degrees. Okay. And we know Fm is 2.374. Go over here to my calculator. So Fm is 2.374 times cosine of 18 degrees divided by cosine of 30 degrees. So we get, guys, it's not too much bigger. It's Fv is going to be equal to 2.607 times the weight of the person. Okay, any questions about that? In the book there, they give 2.3 and or excuse me, 2.4. They round up to 2.4 for FM, and they round to 2.6 for FV. And they do make a note here. Actually, I was wondering about this because it didn't seem right that FV was parallel to the spine. They actually do make some comments here about that. but it's so close to being parallel that the error in calculation for you assuming that it's parallel is so small it doesn't really even come into play here. I'll let you guys read about it in the example. So any questions about that? Doesn't seem like anybody's asking any questions, so we can go ahead and end things there. So I'll stick around here for a couple minutes in case somebody wants to talk to me. Willing to answer any questions you might have had about your test or anything like that if you guys want. I'll since there was free response for this test, I can give you guys the Scantron and the free response portion back so you can see how you were graded. And I'll let you keep that.
I'm just checking. Our lab next week on Monday is in person. Oh, no, sorry. It's at home, and we're not officially meeting in Zoom at a specific time.
We can do a Zoom meeting if you guys want. I'm always open to do like an optional Zoom meeting. So what do you guys want to do? Just gotta tell me.
Like to go over the lab together?
We
Or
can do that. Yeah, sure. I can. We can do an optional Zoom on Monday where you guys can just ask me questions about the lab. Let me pull up the. We go ahead and stop recording, so and then we can